Hello, class. Today's lecture video for chemistry on Tuesday, September 1st. We have two topics we're going to talk about today. The first is identifying controls and variables, and then after that, we're going to talk about graphing for a little bit, do a quick review of graphing. All right, so when I want to talk about identifying controls and variables, it really gets to be about when we're looking at our data. What is it that we are doing? How do we understand our data? The first concept I want to talk about is what is a control group. You guys might have heard about this in other science classes or when you listen to a news report. But a control group, this is simply what's our normal situation, right? Our control group, this is the group of people or the group of chemicals, whatever it is we're studying, that nothing special has been done, the normal, if you will. Okay, we're going to compare our results to this group. We're going to do something to another set of variables, to another group, and we're going to see that what did we do to those? Did that make a difference compared to the normal? So, for example, a drug company, right? If they want to make a drug, we want to cure headaches, for example, right? So we would take our normal group would be, let's just look at a group of people that aren't taking our medicine. How many headaches do they get in a month? And then we're going to take another group of people and we're going to give them our new medicine. And then we're going to measure how many headaches they got in a month. So our normal people, the ones without the medicine in this case, what's their results? And our testing group, the ones that do get the medicine, what are those results? So that's the difference between a control group and that's what a control group means. It's our normal. We don't change our control group throughout the trials. We're always going to compare. We might try a medicine one compared to our control group. We might try a different headache medicine compared to our control group. We're always using that as our baseline, if you will. We're going to use that as our measuring rod. Did our medicine help or hurt, or not do anything? The next thing I want to talk about is a dependent variable. A dependent variable, hopefully by the name, it tells you it depends on something else. And what this is going to be, this is what we're going to measure. So my example I just gave you, the measurement would be how many headaches does our group get in a month? We measured that, right? We measured it and we found out that it was on average 2.4 headaches a person got per month, right? It's something we measure, something we observe, okay? I'll contrast that to an independent variable in a moment, all right? The dependent variable depends on the value of our independent variable. It depends on the value of our independent variable, right? So we took a month. We want to look at over a time frame of a month. For example, how many headaches did a person get in a month? We didn't ask it the other way around. How long does it take for a person to get a headache? Slightly different question, but significantly different. So again, dependent variable is what we measure, what we observe. These are our results. This is what we would say. Here's what we found out by doing our study, our experiment. Now, when we present this data, usually we present this data on a graph. Oftentimes we present it on a graph, and our dependent variable is plotted on our vertical axis, right? Our vertical axis. In math class, you've probably called this the y-axis, okay? Now, I want to talk with you about the independent variable. We talked a moment ago about a dependent variable. It's what we're measuring, what we're observing. Our independent variable, on the other hand, this is what we're changing. This is what we're changing. So in the example I was using of the pharmaceutical company, what did we change? Did you get the medicine, or did you get no medicine, or did you get medicine one? And we could even take it a little bit step further and say, well, maybe we had two headache medicines. So did you get no medicine? Did you get headache medicine one? Did you get headache medicine two? We're changing that. We're changing what medicine the person got or that group got. Right? Another way to think about it is it's what we're testing. Our independent variable is what we're testing. Does medicine one make a difference? Does medicine two make a difference? Does it help people with reducing the number of headaches they get? And we can also describe this as being what we're in control of. We are in control of what medicine each group got. So 3 different ways of saying it, what we change, what we're testing, what we're in control of. I hope you're trying to get all the idea of this is what we're selecting. This is what we want to find out. What does this do? What does the impact does this independent variable have on our dependent variable, in this case our headaches? And our dependent variable is the one we measure. Our independent variable is the one we choose, we test, we control. All right. Now, we talked about the dependent variable being on the vertical axis, so hopefully that makes sense. That our independent variable then is on our horizontal axis or our x-axis, as you learned in math class. All right. A way to help remember which variable goes where, I want to use the phrase dry mix. Dry mix. If you can remember this phrase, it'll help you remember which variable goes where. And by that I mean D in dry, we have D for dependent, Y, it goes on the y-axis. In mix, we have I for independent variable, and it goes on our x-axis. So dry, D for dependent, y-axis, mix, I for independent, x-axis. So let's go through a couple of quick examples. So here we can take a look at our experiment here on the left. Mrs. Rogers thinks that drinking a Monster Energy drink will increase the productivity of her students. She takes 2 classes of 30 students and assigns each class the same task. In this case, they're supposed to copy the statement, chemistry rocks. Of course, chemistry rocks. Put that into their notebooks as many times as possible in 1 hour. Okay, in 1 hour. So there's her scenario. This is what she's going to do. Now, how does she do it? Well, she's going to give class A, she's going to give them the Monster drink while they work. Class B, on the other hand, is not given anything to drink. Nothing to drink. So after an hour, she's going to count how many times the class has copied the statement. So she did her experiment. Group A copied the statement 1,587 times, while Group B copied the statement 2,113 times. So we have our questions over here. These are going to be kind of standard questions we're going to ask about our scenarios. So I want you to be able to understand these questions and how they're going to apply, because I'm going to ask you that on a quiz on Friday. All right. So our standard set of questions. What's our control group? Well, if you remember, our control group is the one, it's our normal. Nothing special is being done to them. Well, in our case, what's our normal? That would be class B, the ones that aren't given anything to drink, because typically you're not drinking a Monster drink, right? So our control group here would be class B. It's our normal group, the group that we don't do anything special to. What's our independent variable? Now, our independent variable is the thing we change. It's the thing we select. It's the thing we choose. It's the thing we want to test. Does this have an impact? Well, what are we testing here? We're testing whether Monster Energy will help improve her productivity. That's our variable. Did you get it? Did you not get it? We're controlling that. We're picking that. Well, what is it that we want to measure? That's what our dependent variable is, our measure. We're going to measure productivity. And in fact, another way you can see it is right here in our description. What did she measure? What did she measure? In Group A, she measured. They copied the statement 1,587 times. There's a number. There's a measurement. Okay. So our dependent variable again here is our productivity, the number of times the statement was copied. The number of times the statement was copied. So oftentimes it'll help you figure out your variable by looking for numbers. What do you see for numbers? What number changed? Right? And then your task then to identify between your dependent variable or your independent variable was that change caused by us, or was that change caused by something we measured? If it's caused by us, something we selected, independent variable. If it's something we measured, dependent variable. So now on to our question 4, should she accept or reject her hypothesis? So I want to go back into the description here. What is her hypothesis? Her hypothesis is right here in the first sentence. Drinking Monster Energy drink will increase the productivity of her students. So her hypothesis is, what's her idea? What's her, what does she think is true and why? Right? I think I can improve my productivity by giving my students Monster Energy drink. Right? So that's her hypothesis, her explanation. Right? Was it true? So let's look at the data. Group A was given the Monster Energy drink. Right? How many times did Group A copy it? 1,587 times. Okay, good. Well, Group B, let's talk what Group B is, our control group. They all copied it 2,113 times. So what happened? When we gave the students the Monster Energy drink, Our hypothesis was that their productivity would increase. What did we find out? Exactly the opposite. Our productivity decreased for our experimental group, our class A. So she should reject her hypothesis here. It did not increase the productivity. How can we improve our experiment? My Lord, there are lots of ways this experiment could be improved. First off, maybe let's even look at time. She measured this for an hour. Can you imagine writing the same thing over and over and over for an hour? That's probably way too long. We're going to get bored. We're humans. We don't do things like that. So maybe 10 minutes would have been a little bit better, or maybe even 5 minutes could have been a better measure of what we're looking at. Okay, so that could potentially be one example. Maybe it's a different task, right? Instead of writing chemistry rocks, right? Your hand gets tired or it gets boring after a while. Maybe we give them a different task that maybe held their interest a little bit more, so we could see if it was not simply a matter of being bored, right? We could have used larger groups. 30 students, that's not a very large group. If we're going to really try to understand what's going on, we'd probably want to do hundreds, if not thousands, of people in a group so we can get a good average, right? When you're talking about 30 students, you could have perhaps your better students in your control group that just happen to be that way. Your better students were in your control group. And so that when you looked at your test group, it's kind of an unfair advantage. They were already more productive. So we got to be careful when we're looking at our groups, and also try to make sure that our groups are pretty much made up of the same kinds of people, right? Where do they live? What's their socioeconomics? What language do they speak? How old are they? Do we have an even mix of male versus female? I mean, there's so many things we could look at, but we'd want our two groups, our class A and class B, to be as similar to each other as possible so we don't skew our results or don't impact our results. We could have also done more trials. What do we mean by that? She measured this once. So maybe she could have done this on Monday, for example, and then on Tuesday she did the experiment again, right? And got some more data, because it could have been that maybe there was a ball game on Sunday night or a concert on Sunday night, and a lot of students went to that. So on Monday they just weren't feeling into it, right? So there was something outside of her control that impacted her trial on Monday. But if she took more trials, let's say do it 5 each day of the week, she'd get a much better idea of what really is going on. Now, question 5 here was a little bit more kind of far out, but I want you to be thinking about experiments a little bit here as well as our control groups, our independent variables, and our dependent variables, because there's a lot that goes into making something a good experiment, and we have to understand these pieces. Finally, a one-step delivery system. So maybe the students, if you think about it, if you're going to be drinking a drink, you need your, what if she gave them the can, right? And they're drinking out of the can. So they have to put down their pen, or they have to let go of the paper, something, but it's going to be a distraction to pick up that can and drink. What if she gave them, maybe you've seen this at people at ball games, right? They got the ball cap and they got the 2 cans of a drink, and they have a straw. So all they got to do is they just drink it right there. I mean, they don't have to move their hands at all. It's like keep writing right all the time. So maybe that was an impact to your experiment. Again, there's so many things we could look at here. Let's do another example. What is the department's initial observation? So this is going to be our beginning of our question here. So let's look at our statement. The Westerville North Science Department notices that the refrigerator is covered in a strange green slime. One teacher comes up with the idea of spraying vinegar on the slime to get rid of it. Yeah, it seems like a reasonable idea. Being the science department, of course we know what we're going to run an experiment. So we're going to check this out by spraying half of the refrigerator with vinegar, and the other half we're not going to do anything to. After 3 days of treatment, the green slime on the side of the fridge that has been treated with the vinegar started to disappear. The untreated side still has that strange green slime. So what is our department's initial observation? It's right there in our first sentence, right? The department notices that the refrigerator is covered in strange green slime. So that's our very first thing. That's our initial observation, right? So then we came up with our hypothesis. I don't have that listed as a question here, but what's our hypothesis, right? That's our second sentence. The teacher comes up with the idea of spraying vinegar on the slime to get rid of it. Okay, our hypothesis, if we spray vinegar on the slime, then we can get rid of it. All right. Our control group, number 7, remember our control group is the one that doesn't get anything done to it. Right? So that would be our untreated side in our refrigerator. Untreated side in our refrigerator. Now our independent variable and our dependent variable, questions 8 and 9. Remember, independent's what we're changing. 9 is what we're measuring. Sometimes it's easier to identify the dependent variable than it is the independent variable. So maybe try that. What is it that we're measuring? Well, if we look in the last paragraph there, those 2 sentences tell us what we measured. After 3 days of treatment, the green slime with the vinegar started to disappear. We measured that. We observed that. The untreated side still had the green slime. Again, we measured that. We observed that. So that will be our dependent variable. Right? We didn't choose that. We didn't choose this side the slime will go away and this side it won't. No, that's what we measured. What did we choose? We chose, do you get the vinegar or not? All right, so our independent variable is, did you get the vinegar? Our dependent variable, that's because we controlled it. We chose that. Our dependent variable then is, how much slime did we see? All right, and finally, step 10 here. What should our conclusion be? Well, we look at we see, what did we see? We saw the green slime disappeared when the vinegar. So our conclusion should be that our hypothesis or our idea was correct, right? Vinegar gets rid of the green slime. Okay. Now, just to keep this video a little shorter, I'm not going to read the scenario this time. So take a pause for a moment, read the scenario, and then come back and we'll go through the questions. Okay, question 11 here. We want to identify the control group. Remember, our control group is a thing that doesn't change. We're not doing anything special to them, right? So our control group here is going to be the group, right? He tells 15 students to use the smart shampoo. The other 15, they don't know about the smart shampoo. So that would be our control group. The ones that don't know about the smart shampoo. Our independent variable here, our independent variable is, what did we change? Did you get the smart shampoo? That's the variable that we changed. Did you not? Or did you get it or did you not? What's our dependent variable? What's our dependent variable? That's the thing we're measuring. So if you look at this, the first test, the students that used the smart shampoo averaged a grade of 87.6, and on the other class measured 87.3. So there's something we measure, and then we can look at that in the first paragraph. It kind of gives us the idea too of what we're going to measure. The smart shampoo claims to guarantee a 10% increase on test scores. Well, how are we going to measure a 10% increase we have to measure that to see that there's an increase in test scores. So again, that gives you the idea. That is your dependent variable. Is this a good experiment? Number 14. Well, there's so many things we could talk about here. We did do 2 trials, so that's good. But 2 trials still isn't a lot. We could do more. We only used 15 students in each group. That's very, very small. We should have used way, way more. Maybe the students didn't use the shampoo long enough. So if you're going to use the smart shampoo, should we give them some instructions? You must wash your hair for at least 10 minutes for this to have an impact on you. We didn't give them any instructions on how to use the shampoo, right? So I wouldn't call this a good experiment. I just gave you some things that might influence that result as well. Okay. Finally, to explain whether data supports the advertiser's claims. Well, if we look at our first trial, in the first trial, the students that used the smart shampoo, 87.6% was their average versus the ones that didn't, 87.3. So yeah, it looks like in the first trial, the students with the smart shampoo did better. But let's look at the second trial. The ones that did use the shampoo got 94.7, but the ones that didn't got 94.9. So in this case, in this particular trial, it looks like the smart shampoo hurt the students. So here we have two trials, and they're conflicting in their results. So I would say this does not support our advertiser's claim. There's not a clear answer here. Another way to look at it is there's very little difference between these numbers. 87.6, 87.3, they're very close to each other. 94.7, 94.9, very close to each other. So even if there is an impact, it's going to be so small, would it be worth paying the extra money for this smart shampoo? So there's a couple thoughts here I want you to think about here. The biggest thing I want you to see in these scenarios, what's our control group? The one that nothing changed, nothing special is done to. In this case, the students that did not use the smart shampoo. Independent variable, what are we changing? Dependent variable, what are we measuring? Okay. And finally, this last question, we're going to add, does Rogaine, it's a commercial product that it tells people to help their hair grow. So this is her task. She wants to decide whether this hypothesis, Rogaine will make your hair grow faster. She wants to see if that's true. So her family is willing to volunteer for the experiment. I'll leave this one up for you guys. Think about this a little bit, and we'll talk about this on Wednesday. The second part of the video that I want to talk about with you guys today is graphing. So here we're going to look at two data tables. We've got example one. We have a table that has time on rocket 1, rocket 2. How far did rocket 1 go? How far did rocket 2 go? And then we have another data table over here for a different scenario, time and mass. All right, so when we're looking at a data table, the thing I want you to look at first, it says a data table on the left side. So this is our leftmost column, right? What's in our leftmost column? That is our independent variable. That's going to be on our x-axis. By convention, by standard, the usual process is our first column here will be our independent variable, which we'll plot on the x-axis. Anything farther to the right, in this case, rocket 1, rocket 2, we have two variables over here. Two trials, if you will, and over here in example 2, we just have that one column. Any columns past that left column, those are going to be our dependent variables. Right, and we're going to graph those numbers on our y-axis, our vertical axis. So it says here on the data tables where we're going to label them. Right, I want you to label the number dry mix dependent on the y, independent on the x. Whoop. So we would label these, right? Our independent variable is our left column. Our dependent variable, here's our left column. Our dependent variable are all the others. Couple rules when you're doing a graph. And this is going to be important because I will quiz you on this on Friday. I'm going to ask you to draw a graph and make your graph correct. Right? Do it in the correct place. So the first, we have a little acronym here, PAST-K, P-A-S-T-K. It's at the top of the screen there. And you see them on the 5 points, so I'll go with those letters in that acronym. So what's P stand for? P stands for we're going to plot our data, right? If we're going to graph, that's what I mean by graphing. We're going to put our data we're going to plot our data on a graph. A, we have to label our axes. So what's on our horizontal axis, our X, what's on our vertical axis, our Y, and we also have to tell what units we are. Right, so let's take a moment and look at our example number 2 here, the table that we have. It says time. It says it's in minutes, 0, 15, 30, 45, 60, 75, 90. Those could have easily been, if we didn't put minutes there, you wouldn't know if I'm talking about seconds or hours or days. We always have to put our units in. Sometimes you hear science teachers talk about naked numbers. That's a number without a unit. We don't like those. They don't tell us anything. Always make sure you have a unit with your number. And we're doing that when we're plotting our data. That means our axes, the y-axis, the x-axis, both those have to have units. All right, x-axis. Remember, that's our independent variable, dry mix. Independent variable mix, independent variable is on the x-axis. That means our dependent variable goes on our y-axis. Again, remember on your data table over here to the right, which one's your independent? Your first column is always your independent variable. Every other column to the right will be dependent variables. Again, don't forget to put your units on your axis. S. This is probably the hardest one here. And by this, if we say scale or spacing. So what I want you to think about here, what I'm talking about here, is when we're making our data, we're making our graph, our data should fill at least 2/3 of that graph paper. Don't make it so it fills up just one tiny little corner. Use the paper, use the space you've been given. You see, your data should fill between 2/3 and 3/4 of that graph paper. I really, really want you to focus on this. This is hard. This is our most complicated piece, but I need you to do this on Friday. I want to make sure you use 2/3, 3/4 of the graph paper. And I'll do an example here in a moment to show you. Key point in doing this to help you is you don't have to start numbering at 0. Now, if we look at our x-axis here, our independent variable, our time, yeah, our time started at 0 and then went 15, 30, 45. But look at our y-axis, our dependent variable, our mass, right? Our highest one there is 19.4. Our smallest one is 16.8. So our range, the data is always going to fall between just 16.8 and 19.4. Why do we need to include on our graph 0? 0 up to 16. Right? That means 2/3, 3/4 of our data is going to be below. If we went from 0 to 20, right, to kind of get our range here, 3/4 of our data, 3/4 of that space isn't going to even have data in it because our first data point starts at 16.8. Don't start it at 0. Let's start it maybe at 16. Right? We have to be smart in our choices of how we label our graphs and the scale, our axes, the numbers our axes start from and end on. All right, T, title. Hopefully that makes enough sense. Every graph should have a title. How do we want to format our title? List your independent variable and then your dependent variable. So if I would look at the example number 2, that data table at the top, I might say time impacts on mass. Right? List my independent variable and then my dependent variable. Time impacts on mass. Okay. And finally, K for key. What do I mean by key? So if we have more than one set of data that we're plotting on our graph, how do you know which data points go with which set of data? Right? And we only do this when we have more than one set of data. If you only have one set of data, no key is needed. So let's do an example. Right? Well, sorry, one more thing here. When we look at a graph, there's two things. There's one thing we can look at, answer right away. Is it a direct relationship or is it an indirect relationship? If it's a direct relationship, that means our line goes up. So our slope's up. So as you move from left to right, our line will be going up. As the independent variable increases, we're moving left to right. The dependent variable, our y-axis, also increases, so our line goes up. I want to contrast that to an indirect relationship because it's exactly the opposite. Right? So in a direct relationship, both variables increase. In an indirect relationship, our line goes down. It slopes down. That means as our x-axis, our independent variable increases, our dependent variable decreases. So our variables here, x and y, independent, dependent, they're going in opposite directions. Same direction, we call it direct. Opposite directions, we call it indirect. All right. So let's look at these 4 plots here. Let's identify whether our graphs are indirect or direct. If we look at our one on the left, life expectancy, hopefully you're just looking at that, it makes sense. The more cigarettes you smoke, the less you're going to live, the shorter you're going to live. Our line is going to be sloping down. That would be an example of an indirect relationship. Right? Next one to the right, relationship between money and problems, slopes up, direct relationship. Right? More money you have tends to mean you have more problems. Let's look at the B, the one down below for ice cream sales. Again, the higher the temperature, the more ice cream sales. Hopefully that makes sense. In January here, when it's cold here in Columbus, there's probably not as much ice cream sales as there are in August when it's very hot. Right? The line goes up. That's a direct relationship. And finally, ticket price versus attendance. Think about that. If the ticket price is low, more people are going to go. If the ticket price is high, less people are going. And finally, let's look at the ticket price one. If the attendance is low, that means your ticket price is going to be high. And if your attendance gets bigger, that means your ticket price is probably going to be smaller. So we have that downward slope, negative slope. We will have an indirect relationship. Okay. Let's do an example for our graph. For our graph here, let's go back. We're going to use the data on our first page, and we're going to put all of our information on here. So PASTK. We're going to plot it. We're going to label our axes. We're going to make sure we have it scaled to fill as much of our screen as possible. We're going to put a title, and we're going to put a key if needed. So quick reminder, here's what our data tables were. Right? So what I'd like you to do is take a moment and plot example 1 on a sheet of graph paper. And if you don't have a sheet of graph paper, just make one. Just draw some squares or some lines on a piece of paper, and it'll make it. It's easy to do. All right. So here, this is an example of what this graph would look like. Right? We took the data table number 1, and we saw the time went from 0 to about 36 rather. So we made our graph, and we fit our data points onto the graph. Now if we would have counted on our graph how many lines we had, we went 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So we have 20 steps we can take, but we got to get, our data has to go up to 36. Our data has to go up to 36. So let's take 36, and we're going to divide it by 20. And what do you get? You're going to get 1.8. Right? Now, we're going to take that 1.8 and we're going to round it up. We're never going to round that number down. We're going to round it up. And we're going to round that 1.8 up, and it's going to go to 2. Why is this important? Because that tells you how many each tick mark here on your x-axis is going to be. 2. Right? So we took how much of our range. We had to go from 0 to 36. Our range had to go for 36 on our x-axis. We had 20 steps we could take. We take our range, 36. We divide it by our steps, 20. We get 1.8 is our answer. We have to round that up. When you round it up, that tells you how big each step here is going to be. That'll help you effectively fill your graph for our scale. Let's look over here on the left, right? If we look at our data, I think went to 95. Or 98 was our highest data. You see that here at 36 seconds for rocket 1. So we have to go from 98. What's our smallest number on our y? It's going to be 0. So our range here is 0 to 98. That's how much we have to span on our table. How many steps do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So we have to go 98. We have to accommodate that range of data, 98. We have 20 steps to get there. What are you going to get? You're going to get 4.9. 4.9. We're going to round that number up, right? That number is going to round up to 5. So that means each step on our graph here is going to be worth 5. All right. We're starting at our lowest data point, which is 0. So we're going to start each label. We're going to start at 0 and then increment 5 each time we go up. Okay, so here we've done 2 things. We first had to figure out what our scale was, but how do we fill our paper? And we did that by what was the range of our data on the x-axis over how many tick marks do we have? What was the range on our y-axis? How many tick marks do we have? And we divided our range of our data by how many tick marks, and then we rounded that answer up, and that told us how much each tick mark on our graph should be. Now we're going to effectively use most of our space here. So once we have our axes labeled with our numbers, let's go ahead and put the labels on their axes down here in the bottom. Right, our independent variable goes on the horizontal axis. We're measuring time. If we look at our data table, we see that time was measured in seconds. So we're going to put that down here in our label for our axis. Similarly, for our y, we know that our y, we go back up and look at our data, it's distance, and we did it in meters. Whoop. We put distance in meters here for our label. Then we plot our points. Now, if we have 2 sets of data here, so we have to be careful as we plot those points. Right. So we're going to you can do this so many different ways, guys. And here's 3 different examples. We can have one set of data be in pink, the other set of data in yellow. So you can use different colors. We could have them being different shapes. One set of data has stars. One set of data has circles. We can connect the data points in different ways. Here they're connected with dashes. Here they're connected with solid lines. So there's so many different things you can do to distinguish one set of data from another. And we did all 3, color, symbol, and the line connecting. Right? And so if we have 2 sets of data, we need our key. And we labeled our key down here. Rocket 1 is yellow with a solid line and circles. Rocket 2 is pink with stars and dashed lines. The final thing we have to do is put our title on here. Right? We're going to label our independent variable time versus distance. Right? And distance being our y-axis. So there's an example of a graph for you guys. We'll do some more of this tomorrow, and again, this will be on our quiz on Friday. All right, that's it for today. Thanks, everybody.